So we are very happy to have Thimo Preis. He's visiting us for an extended period. And today he will tell us about solving strongly interacting scalar quantum field theory in 4 dimensions. Please.
Yes, thank you for the introduction. Thank you for coming. Thank you also for having me for this extended visit. I'm very happy to be here and I've enjoyed my visit a lot. So since on my last visit in September, in the Cardinal seminar, I already talked about the major thrust of my PhD work, which is about self-similar quantum many-body systems out of equilibrium, as in ultra-cold atom systems. I decided that I take this opportunity today to talk about an ongoing work, which is based on a recent work we put out and then an ongoing publication which we hope to put out in the next weeks. And in that sense, I really would like to encourage you to ask a lot of questions because I condensed the slides to really represent the physics of this model that I'm going to talk about and would like to hear your thoughts about what you think about it. And if there are any technical questions, I can just always jump in the backup slides and give you more details.
The date is wrong.
The date? Oh,
Because that is
That's the European way to write.
my apologies. I did not realize. Okay, so as for my introduction, so I want to, this work originated in a long-standing interest to study real-time dynamics of strongly coupled theories with a scale-dependent coupling, which is currently very much out of reach for many systems in 4 dimensions. And today I want to describe to you a model which possibly has some applications as a laboratory towards this, studying such strongly coupled dynamics in real time in 4 dimensions. And the basic first step is that strongly coupled scale-dependent physics is usually associated to asymptotic freedom as a cornerstone of a fundamental description of nature in the standard model of particle physics. Of course, the most important example is asymptotic freedom in the theory of quantum chromodynamics in 4 dimensions, where the idea is that we have to consider the renormalization group flow of our system, meaning that we are interested in the question of how do quantum fluctuations impact the correlation functions, interaction strengths at the scale at which we are probing the system. And asymptotic freedom is then the phenomenon that the interaction strength of our fields that we are considering decreases as we increase the interaction strength, or vice versa, as we decrease the length scale of the problem, of the microscope with which we are probing the problem at hand. This means that the interaction strength decreases towards the ultraviolet, towards larger momentum scales, and perturbative methods become increasingly more applicable, which has led to a plethora of different, perturbative QCD calculations, predictions, which have been confirmed at various colliders. And in particular, the asymptotic freedom behavior of the strong coupling has been confirmed also over the years after the initial prediction more than 50 years ago by a wide range of different experiments. Now, if you go the other direction, right, if you follow the asymptotic freedom towards the infrared, you see that the coupling grows. And in particular, perturbation theory tells you that the coupling diverges at a finite momentum scale, at a finite length scale with which you're probing the system, which is usually called lambda QCD. And the idea behind this, or the usual understanding, is that we have the phenomenon of dynamical transmutation happening where a theory that is originally massless, such as Yang-Mills theory, just the gluonic sector, quantum fluctuations generate a non-perturbative scale that has to be taken into account where new physics comes in. And the new physics is usually associated with the phenomenon of confinement, such that the degrees of freedom that you're initially considering, so perturbatively free gluonic fields, are not the degrees of freedom of your system anymore, it's extended objects, and you have to consider composite fields, you have to consider other correlation functions as the driving degrees of freedom, giving you an insight into the growth of the coupling. However, in general, the statement is that you cannot follow the strong coupling or the growth of the coupling towards any scale in the infrared. It just becomes ill-defined, and you have to consider other quantities to make sense of the physics. So in that sense, it would be very valuable if we have a laboratory not saying it's a physical system, but a system in 4 dimensions where you can study such physics, strongly coupled physics, asymptotically free physics, from over all length scales, over all momentum scales. And this is what I would like to propose today. A laboratory where such asymptotic freedom is realized and strongly coupled physics can be studied over a wide range of different length scales, or all length scales, in fact. And the starting point for this is the advent of so-called tensor field theories, which gained a lot of interest in like the last 10 years or so, where it was shown that, so if you have a field theory where the field is in a fundamental representation of some tensor group of rank R, and the rank is now larger than 2. So not a vector theory, not a matrix theory, but a tensor theory, that actually the subset of these theories possess a very non-trivial large N limit, which is well controlled, analytically well controlled. In contrast to matrix models where you don't know how to resum planar diagrams, the tensor theories allow resummations and are non-trivial already at leading order. And this spurred, like this insight, which came initially in 2011, spurred a lot of interest in the following years, which mainly go in 2 different directions. First, in 2016, Witten remarked that the melonic limit, so the large N limit of these tensor field theories, such diagrams are depicted here, and melons being, it's called melons because there are all these round objects here, being the self-energy insertions into your correlation functions, that in the large N limit, they map to the large N limit of the SYK model without disorder. And this has led to a lot of interest into studying these theories and also the holographic duals of these theories. And then on the other side, this was on the other side, in 2016, 2017, Klebanov and Tarnopolsky started the avenue of studying this tensor field theories also in 3+1 dimensions, 4 Euclidean dimensions, looking for new renormalization group fixed points. And what they found is that in less than 4 dimensions, or the theories they studied, they found no fixed points, so-called melonic conformal field theories, corresponding to melonic conformal field theories, which have different phenomena, and usually, now the initial works, they found a scaling solution and found fixed point values in less than 4 dimensions, but since you have a tensor theory, you have multiple couplings that you have to consider, and some of the couplings turned out to be complex at the fixed point, which means that the conformal field theory is unstable. And then like further research into other versions of these models, because people are just starting to build these models. Many models, tensor field theories exist with these non-trivial large N limits. People are continuing to investigate different possible models that yield non-trivial dynamics. And today I would like to also propose one particular instance of such a model where, since you have this non-trivial large N limit, which is tractable, meaning your closed expression, I can write it on one slide, I can solve this on a computer. And this tensor field theory shows asymptotic freedom of all the quartic couplings. And which means I can solve the equations now on the computer in closed form in the large N limit for different renormalized masses. And whilst, as in QCD, the perturbation theory tells me there's asymptotic freedom, everything decays towards the UV, which you also see here, just the couplings decrease as we go towards the larger momentum scales. There's a finite scale in the infrared where the coupling diverges. So this was very important to us to solve the theory non-perturbatively outside of perturbation theory to see whether the coupling really indeed does diverge. And it turns out that's not the case. For a range of masses, you see that the coupling actually grows and then levels off depending on the mass scale of the system with which you're probing the system, or conversely, the inverse correlation length with which you're probing the system.
So there is a fixed point or no? It's just
probably not.
Probably.
Let me come to that. So the interpretation comes towards the end. What I want to, like in the initial slides, I want to basically show you that this theory seems to be well defined over a wide range of masses, where you can, so for these masses, or many different ranges of masses, you find that the theory, you can solve it over any momentum that you want, and you can solve all the correlation functions and make predictions and these kind of things. So you can study it. However, when you're interested in fixed points, you have to be a bit more careful, and I will come to that towards the end. Okay.
Is the first author in the references?
Bonson. Bonson. So the others are Gourau and Rivasseau and someone else. Yeah. Maybe one more point. So this started, I mean, these studies started already in the 50s and 60s, so to speak, with random matrix theory, where people were interested in the random matrices, which then led to the study of quantum gravity in 2 dimensions in the 70s, 80s, and so on. And then people were looking for higher dimensional generalizations of these models, but they couldn't find a large n limit for them, so they couldn't really use them. But then 2011 came along, and this new large n limit was found. And since then, there's been more interest in these models, since they're controlled in a non-perturbative limit. Okay. So now to the model that I want to discuss. It's a tensor field theory with a global ON cubed symmetry group, which means that the field that we are considering is in the tri-fundamental representation of your global symmetry group. It has 3 indices, A, 1, 2, 3. Each index goes from 1 to n. With the corresponding action here, this is the action of all the bare values, so bare fields and bare couplings. I will talk about it in a second. This model was, or a version of this model, not this one here, but a version of this model was first started in these 2 works by Karosa, Tanasa, and Klebanov-Tarnopolsky. So it's sometimes called the CT-KT model, where these melonic fixed points and so on were discussed. But today I would like to talk about a different version of this model. So let me first start off. So we have this field where I group all these 3 indices into a super index. And then you want to look at what are the quartic invariant interactions that you can find. And it turns out there are 3. So these 3 I show here. I mean, the equations for them are shown here with their projectors. They are respectively called pillow, double trace, and tetrahedron. And where the pillow is just, you have some sort of, so to speak, a trivial contraction within the 2 pairs and then one non-trivial across pairs. Double trace is just you have 2 trace singlets, so to speak. And then the tetrahedron is the interesting one, where all the different fields are connected with each other. And this tetrahedron contraction pattern will turn out to be the non-trivial one that drives all the flow. And this is also the one that is basically the interesting one for all the tensor field theories that people study usually.
Are you assuming large n?
Not yet. Later on. I mean, this is why all these are already normalized with the respective n values.
Are the couplings corresponding to each of these 3 cases?
Yes. So, in particular, I use a linear combination of these 2. So the couplings, this would be called this GP pillow. Double trace is GD, and tetrahedron is just G. But it turns out that the projectors are not orthonormal in this space. So one does a linear combination usually. I mean, they don't look as nice as these. So I show this, but in practice I use GP plus GD, pillow plus double trace, and then GP over 3. It's just a change of basis in the coupling space.
Symmetric.
Yeah.
So are these the only thing that is symmetric under ON cube?
Mm-hmm.
The only.
The symmetry is just ON, right?
ON cubed. ON, tensor product ON, tensor product ON.
I have 3 ON.
Yes.
3
copies.
different ON.
3 different ON. But how does it act on, so let's see, phi is symmetric.
Mm-hmm. So I mean, so it acts with 1 rotation in each index, so to speak.
Tri-fundamental representation.
Yes, exactly. Tri-fundamental.
So always the index with the A2 always contracted with either C2 or B2.
Yes.
It doesn't contract with B1 or B3.
Okay, so phi is not symmetric in the indices.
No, it's a tensor product, right?
Yeah, exactly.
It's a tensor product,
Tensor product.
3 vector fields.
Okay.
Yes, correct.
So it's not, you can't communicate.
You can't-
Not among the indices.
Not A1 with A2.
Sorry, I
they
misunderstood.
can't.
Yes, that's correct. And now comes the crux of the problem, why I get asymptotic freedom. And this might, this might pose a lot of questions, but let me, expand a bit on it.
So what is that imaginary thing?
Yes, exactly. One of the couplings is turned imaginary.
Is this
And-
why it escapes all this no-go theorems?
Yes, exactly.
What are the
Well, isn't it some theorem that the only asymptotically free series are?
Yeah, there's like the price of asymptotic freedom. There's like a paper.
This is what Groth and Wilczek tried to prove.
Yeah, and they show that it's basically just non-abelian theories, but they assume that the coupling is just positive real. And then, I mean, I will talk about it later on, but then shortly after, this was called Price of Asymptotic Freedom, I think in like 75 or 76. And then shortly after, Szymanczyk tried to find asymptotic freedom in scalar theories with a negative coupling, which avoids this no-go theorem. But those are not bounded because you just have one, quartic interaction with a negative coupling, not a bounded potential. Here, the crux turns out to be the system. I mean, as I will show in large N, or even in perturbation theory in large N, is well defined because you have two other couplings. And they will turn out to be always positive real, and they bound your potential.
And somehow still, sorry,
Go ahead.
even with this imaginary coupling, it's still unitary.
I mean, this so far I'm not making statements about it. I'm saying so the Hamiltonian is not Hermitian. That's true.
Correct. That one.
Yeah. That's true. But what will turn, I mean, let me elaborate on the next slides. What will turn out is that the path integral is bounded and the effective action is real in the large N limit. So you can still make sense of the theory. It's just, I mean, currently I will talk only about Euclidean space. I don't know anything about Minkowski space so far. Yeah, but the quantum effective action in Euclidean space and what I mentioned is real in the large N limit. So, okay, so this to set the scene. Let me first start off with perturbation theory, and then I go on to large N, the large N description for the non-perturbative infrared. So for perturbation theory, we're interested in, I'm now skipping the real case, where you usually just have triviality. You know that ON model is just trivial, just the coupling grows as you increase the momentum scale. And then since you have 3 copies of ON, you just have the same thing in all the sectors in principle. However, it turns out something non-trivial happens as you turn one of the couplings imaginary. And to see this, let us study the beta function, which just encodes how quantum fluctuations change the interaction strength as we change the scale. This you can compute, and you find that the tetrahedral beta function decouples from the other two, G1 and G2. And so if you have a real coupling, this is positive, and you just have the triviality again. However, if you have an imaginary coupling, this is G cubed in comparison to lambda squared in usual 5-4 theory, as I will say later on. Then this turns negative, and you can simply solve it. You find that this is just a standard, logarithmic decay in asymptotic freedom that you are familiar with. Here, where I integrate this equation from some UV scale lambda down to some IR scale mu, and then I can change the scale. And then you see from this equation that as I approach lambda, this equation just approaches 1 from above. And then separately, the beta functions of G1 and G2, they decouple from the tetrahedral flow. And they couple among each other, and then they are driven. So solving the tetrahedral function enters beta 1 and beta 2. So we can look at the RG phase diagram, so to speak, in perturbation theory already. And this is shown here. So these are just stream plots where the different curves correspond to the different trajectories of the vector field, where the arrows point towards the infrared, towards smaller and smaller mu scale. And importantly, there are 2 separatrices, so this red curve and this black curve, which divide the phase diagram into different regions. And between these 2 separatrices, you find that the flow goes towards a non-trivial, strongly interacting infrared, okay, in perturbation theory. And in particular, you can find that so beta 1 and beta 2, they go to 0, and G1 approaches 1. It's not really shown here because I cut off here some scale, but it goes to 1, flattens off, and G2 goes to 3/5.
Can you remind us where does G go?
So G just grows or decays. So in the UV it decays, and G.
So G goes in the UV, it goes to
0,
like asymptotic.
That is the beta function.
Yeah.
But it's complex. It's imaginary, right?
In the
Remaining imaginary, but goes to 0.
I mean, if you solve this equation, then of course it looks real, right? Though this equation just has a pole at some finite momentum scale, as in standard perturbation theory, as in asymptotically free theories.
Sorry.
But it is real, because, I mean, the crux is basically that only the square of the coupling enters all the equations. So even though I have an I, it's always real because only G squared appears, and it's just a sign of flip the sign.
But this G is the imaginary part of the coupling.
Sorry. Yes. Yeah, that's correct.
It's I times G.
I times G. Yeah, correct. Sorry.
So, you know,
That's I agree.
So, but usual phi-4 theory would have the same thing.
No.
No.
You need a G cube, I think.
Yeah, exactly.
It's
So,
as in a free. It's a free theory.
I mean, I will come to it in a second.
You make that
It's lambda
coupling
squared.
I.
It's
So-
lambda squared.
You do it.
You want to have G cube on the right hand side.
Yeah, but if you take
Ah,
IG phi-4 theory, is that
No,
going to be the same?
beta lambda is lambda squared.
Yes, exactly. The
You
beta
want-
function
you
is
want
quadratic.
Beta function to be cubic.
Then it doesn't work. Then it's just imaginary. Because it's cubic, because it has very like this is with this non-trivial large n limit. This leads to it to being cubic, and then it works out
There
somehow.
is no diagram that
Exactly.
normalized
Yeah.
here.
It's just basically the idea would be that the whole flow is driven by the wave function renormalization, which is just this melon, this sunset diagram, basically.
But still for lambda phi-4, if you chose it to be neither imaginary nor real, but complex in some direction, maybe there would be, like if it's
Some real and some complex part, you mean?
Some
Yeah,
root
like a
of
cubic-
unity, which is
cubic
not square root.
yeah, cubic root of
I see.
Something like this.
Mhm.
then it would be in this direction, it would be asymptotically free, right?
Yes,
but it's probably non-unitary.
yes, and non-bounded. That's probably, that's the thing.
Give it up on.
Yeah. Basically, I mean, the current, as far as I understand, the current knowledge is people have given up on single component theories for this, for some scalar theories to study asymptotic freedom, apart from PT symmetric theories, which also have such interpretations to make sense of them. But that's a bit, tricky to understand. So, which is why we're going to higher component fields, basically. I'm not sure whether it works for single component fields.
So this going to 1 and approaching 3/2, that is approaching in the UV or in the IR?
IR. So the flow or the arrows
IR.
point towards the IR. Yes. And conversely, so if you invert the arrows, you flow to the UV. So you see that all the couplings go to some Gaussian UV fixed point. All the 3 couplings go to Gaussian fixed point.
but what happens at the Landau pole?
There is none, right? It goes to 1.
I mean,
No.
But G goes.
No, no.
yeah, no.
G
I
has
mean, yeah, G has a Landau.
Okay, not G1.
For this, we solve the equations non-perturbatively, because of course this is just perturbation theory. You shouldn't trust these equations after some level, after G is large enough, right?
Is your Landau pole in the ultraviolet or the infrared?
In the infrared, it's asymptotically free. So you see this from this equation, right? Round up, this is the pole, and it's in the infrared.
Your UV fixed point, in some sense, is a non-unitary CFT of some kind, or non-unitary scalar invariant theory? You're going to finite G1, G2, and your
The
G is
UV
going
is
to
free,
0.
the UV is free and unitary, and he adds a
It
non-unitary.
doesn't look free
Yeah.
though, because G1 and G2. are
No,
also-
but this is the IR. So this is IR.
This, well, I thought the other
So
way
if you
around,
invert the arrows,
they're all running to 0.
Typically,
yeah, they're all about very.
They all
So as
want
you
to-
see, these arrows, if you invert them, they point to the IR, but they all go to the 0 point here. So they all go to.
So really it's a
fixed
free
point.
theory, so.
Yeah,
that's-
just free
that's
theory in
a
the
free
UV.
theory, okay.
the red. Yeah.
Yes, they're head point.
If not, they tend to diverge, right? So
Yes. So
you need to-
along these.
depart a little bit from.
That's correct. So like along basically, I mean, the theory is definitely well defined, or it seems to be well defined along the red separatrix.
Right,
And then, in between them, you
in
find,
between is.
yeah, exactly. There's one trajectory.
But the IR fixed point is still non-unitary, right? Because
I didn't say anything about an IR fixed point.
Yeah,
I'm talking about the strongly interacting IR so far.
Okay.
Let's talk, let's go to the, to the numerics to see what the IR does.
So you mentioned PT symmetry, your theory does have this,
No, this does not have this. So I don't have this argument.
but what is the advantage of this versus the lambda phi-4 that we use? Why do you propose this model?
Because I have a non-trivial large n limit to actually solve the equations. I can solve it completely. And study the scale dependence on that. It seems to be well defined at least.
You can also do it for 5/4, right? The second component. real.
Yeah, but the 5-4 theory is in leading order large n is just trivial. You just have these local daisy cactus insertions, and that's just a mass shift. The theory doesn't even thermalize. So there's nothing going on basically. So this theory is really non-trivial. It has a leading order, the sunset diagram, so it has everything you need basically at lowest order. But I'll come to that. I'll come to that. So just on this argument of that the theory is well defined, I showed you just the stream plot of the different couplings, and here I show you just the flow of the different couplings versus renormalization scale. Since the flow is this logarithmic flow or square root of logarithm in the tetrahedral coupling, you see that it's really, I have to go to like over large orders of magnitude to really resolve any of the physics or any of the flow to see some significant change. And then, I mean, as I showed you before, and this is the flow along the trajectory which defines the red separatrix, so which goes from the UV fixed point to the infrared.
What I didn't understand properly is why when you go to the red, so at some point, the beta functions of G1, G2 should be affected by G and start to grow to large values.
That's
And doesn't look like.
No, they seem to go to a fixed value. I mean, as you increase G.
Does this red curve go all the way to infinity at finite mu?
In the perturbative case, yes, it has this pole, which you don't see here, but this pole.
But then
It has a lambda pole in the infrared, so this pole, yeah.
But look at the beta functions there.
Yeah.
Beta function. This.
They seem to grow with
As you make G larger, you can just factor it out, and then you see that there's a fixed point. You already see it here.
That is the point.
You see it exactly. You see that here 5 minus 3 is just
Sounds
mechanical.
Sounds good.
Exactly.
There is where the 1 and 3 fixed.
So if you follow exactly the flow along this red separatrix, so this is what this trajectory is what I'm plotting.
So you need to fine tune these couplings G1 and G2 in order.
No,
you
doesn't
don't.
seem to need any fine tuning.
No.
It's the other way around, that it's
Yeah,
actually
it just flow to there.
flows into that.
Yeah, into the infrared, exactly. In between these two separatrices. Yeah.
But then when you cross the Landau pole,
I'm not making statements in this regime because this is just perturbation theory. The perturbation theory does not apply. So I'm just talking about the flow roughly. I will in the next slides I will talk
you are
about,
still at the
so to speak, in the UV. Yeah, I'm just
UV side of the Landau pole.
yeah. So basically, I mean the structure of the slides is we had first a paper on the UV perturbation theory, and now we're doing numerical infrared of perturbative, which is where the arguments currently come from. Exactly. So this is just to say that the theory seems to be well defined in the UV. Where if you follow this red separatrix, so you see that all these couplings, so G1 and G2 especially, go to positive constant values. Okay, G seems to grow, and then you might be worried that the path integral is not bounded, but at least you can get a bound. Since this is a complex integral, you have some complex part here, IG, you can just approximate it by the path integral with the real action. And since the other couplings are positive and real, it's bounded. And this is exactly the crux, because in usually, one component or vector models, you have just one coupling, and then you can't do anything. You cannot you cannot tune one coupling and keep the other ones well defined. This is just allows you, so to speak, to keep it well defined. So in that sense, there's at least an argument along the red separatrix that the theory seems to be bounded and well defined. But since you have an imaginary part in your action, you cannot do a standard importance sampling lattice constructions. So we will now use large N methods to study this model. In the strong interacting infrared. Okay, so this is just an introductory slide to large N methods, so the first advent of large N proposals came from a Tilft in like 74 for the Young-Mills theory, and then was used to solve the Tilft model in 1+1 dimensions meson model, and then was studied in a plethora of different systems as one tool, as one of the major tools to study non-perturbative dynamics. In particular for vector models, linear sigma models, or these ON models, these kind of things. This has been the workhorse of statistical physics especially by Saint-Justin, to study all different kinds of systems. And these exactly have this large n limit, which is where you just have these local insertions of tadpoles. So it's just like sometimes called daisy or cactus insertions. But since it's just these local insertions, they don't give you any like non-trivial physics. It's basically some Hartree-Fock, in Conrad's meta language approximation in the dynamics. And then if you increase the theory complexity of the theory a bit further, if you go to matrix models, then things become very complicated. You have these planar diagrams where you don't know renormations only in special systems and special cases in low dimensional systems also. So then people don't really know how to handle this in the infrared. But then somehow it turns, and then you might expect, you add one index further, that it becomes more complicated. But somehow there's a magic of these large and tensor models where it actually becomes easier again. And they have a non-trivial model, non-trivial large n limit, which is called melonic limit. These are diagrams of this resummation. Like the melon comes exactly from, this is the central diagram. So this is an effective action or energy diagram. So if you cut one line, you get the self-energy diagram, which is just a sunset diagram. And you see here that these are the insertions as you iterate the equations, and you can just resum all of this non-perturbatively. So just as an example, I included this diagram here to do the counting with all the indices and everything, just to visualize how this works. So this diagram here has two tetrahedral indices, which are these two, which I showed you before. They both scale with n to the minus 3/2. And then you connect them via propagators here, which each carry 2 super indices or 6 indices, because they have 2 fields each in the tri-fundamental representation. And then all of these, they all identify or contract 3 indices on the left in the vertex with the right vertex. And then if you follow all the closed curves of indices, so for example, you go start from A1, A1 is associated with A1 prime, goes to B1 prime, goes to B1, and then you go through all the indices. You can count one n factor per subindex or n cubed factor per multi-index, and then you find that this is the overall counting. And this turns out to be the relevant diagram in the large n limit. Yeah. Okay. And then to make this more concise, we use effective action formalism, free energy. We write down the free energy function of the theory. Here's a 2pi effective action, 2-particle reducible effective action, where all the diagrams are connected after cutting 2 lines. And in particular, in large n, these are the relevant diagrams. These are just the standard terms, these 2. But then these are the relevant diagrams that contribute. There's one which is a local insertion of these G2 coupling, and then there's one which has these 2 tetrahedral couplings. And in particular, G, the tetrahedral coupling, which we turned imaginary, just appears as a square, which means that there's this flip in the sign in this effective action, and the effective action itself is real, which means that all the correlation functions you compute from this effective action also are real. And
what is a bar?
So these are all currently still bare quantities. I will go through, so this is just the bar is supposed to denote always everything is bare. Renormalization comes in the next slide. And just to show, and then you can, so there is also next to leading order, of course, which is suppressed by 1 over square root of n. You can also talk about it later if you're interested. And then the correlation functions, the dynamics of the correlation functions follow simply by extremizing the effective action, which are just Schwinger-Dyson equations. And the Schwinger-Dyson equation for the 2-point function, for the full resummed, full thing, 2-point function propagator, is just this expression here in bare quantities. And this is basically, the I that I added is just the sign change here. And just to illustrate this, this fact, in standard ON models, what we always study, what I also study a lot, is basically you just have here the same coupling as here. You have a lambda here and a lambda here, and then there's a minus sign here at 2-loop order, sunset approximation. But basically the only difference is here that you have a non-perturbative theory, you have a different coupling here and a plus sign here. But this already resums in infinitely many contributions in the coupling. And so you can solve this equation. Yes. Okay. So now I presented all the bare arguments for the bare theory and the perturbative arguments. So now I would like to go to renormalizing the theory and really studying it numerically in full glory. So we have the bare fields, the masses, and the three quartic couplings that we need to renormalize. We need to provide renormalization conditions at some energy scale, which the experimentalists know and where they can access the quantities of interest for us to define the theory. And so I specified 2 here, but there are 5 in total. So one is, of course, we have to fix the renormalized mass, which we fix in the infrared, as the gap of the 2-point function. And then this is the fixing the wave function renormalization, which relates the bare field with the renormalized field. Notice that there's usually, you might be more familiar with an expression where you have a dp squared there, so derivative with respect to the momentum. This is the same thing, basically. It's just, the only idea is to project out the non-trivial momentum dependence. And this is more stable numerically, so we use this to renormalize the theory.
Is it supposed to be the limit of mu, or is it at all mu? This
is at 1 mu. So the wave function renormalization is this one, and I fix it to be 1 at mu. And mu is some scale in the UV, where I ask the experimentalist to please give me some input. And then I can get the flow, how the quantum fluctuations correct all the correlation functions at all other scales relative to this mu. Then, of course, I have 3 quartic couplings, so I have to provide also renormalization conditions for them. I did not show them here just to not have too much notation. It's just for the 4-point function in each channel, I just set it to a value that I get from experimentalist at mu. Okay. Which will be this G of mu here for the tetrahedral coupling. And
Very good experimentalist.
yeah, I have my hopes up. Then there's one more ingredient before I write down the final equation, which is this one, namely that at large n, there's another feature of these melonic theories. So I have 3 couplings, and at large n, the main coupling, the tetrahedral coupling, does not receive radiated corrections in the sense that it does not have a counter term. So if I write down the 4-point function, it just has the wave function renormalization term, but there's no other corrections to it. So it's purely driven by the wave function renormalization, which is this equation, whilst G1 and G2 have counter terms. So they have, the 4-point function has some beta equation, which you have to solve non-perturbatively and so on and so forth, which remarkably leads to the, all these ingredients come then together to that you are able to write down one equation which describes the full renormalized, resummed and renormalized propagator for a given tetrahedral coupling, which itself is determined, the flow of itself is determined by Z, the wave function renormalization, which only depends on the 2-point function. So you can solve the whole system, the propagator and the tetrahedral coupling in of itself. And since we already saw the G1 and G2, they decouple, or G decouples from G1 and G2, you can then solve G1 and G2 later on separately. So this is what I will talk about today, how we solve this equation, basically, for given coupling G of mu. Notice that before we had, we go back 1 slide, we had here this local tadpole insertion of G2. This is just subtracted by the mass renormalization, because you're just adjusting the bare mass. So, and then in total, you just have renormalized mass, trivial momentum squared, your renormalized coupling at some high UV scale, and then you have, so this is the sunset, this is the subtraction from the bare mass adjusting the bare mass, and then this is the subtraction from the wave function normalization. But this equation you can put in the computer and just solve it iteratively. So the approach that we do here is that I start from some UV scale, where I know that the propagator is bare. It's just 1 over p squared plus m squared. So I just set this to 0, and I plug this into the right-hand side, compute everything, get something in the left-hand side out, plug it in again, and just iterate until it converges below some threshold point-wise, I check. It's like 10 to the minus 7 or so in the deviation. Yeah, but from this point of view, you can solve all of these dynamics for in closed form in the larger internet fully. And this is what
can you prove that doing something like this would never give you a phase transition? That nothing,
Let me come back to that. Yeah, because something happens later on if I solve these equations. But I mean, at least in I guess certain minima, you can always, if fixed point iteration applies, if you have some fixed point, then you can find it by this method. I mean, of course, I guess ideally you would do some Newton looking for zeros of this equation. But yeah. Okay, so let's go to numerically solving this equation. As I said, I provide a coupling in the tetrahedral coupling in the UV at some high UV scale, and then a renormalized mass. The equations will be discretized on a grid, so it's a p-squared grid and one angle that I have to take into account. So I have in effect, I have an IR and a UV cutoff, but if I then of course I check that everything is independent of these cutoffs. It's not a lattice theory, so there's no, the theory is defined in the continuum, and then I just impose cutoffs as I solve the equations. And I just wiggle the cutoffs to check that everything is independent of it. So this is the object that I'm, of course, solving for. This is just a propagator where I scaled out the trivial p-squared dependence. And what I will do always is I solve this equation for a given renormalized mass, and coupling here in all of these slides is always 20 at mu. So I already started a rather large value, because otherwise I have to solve over, I don't know, 15 orders of magnitude on a grid. And this, it's very difficult for good accuracy, even on a supercomputer, because in many points the result is very accurately in the infrared. So I will always compare also to perturbation theory here, which are the dashed black lines, which you get from two-loop perturbation theory. The result here is shown here. I can show you later how you get this. But basically, it's just you have some, correction, some non-trivial momentum dependence, which comes in on the wave function dependence. It's exactly this log running of the tetrahedral coupling, which comes into the two-point function. And this leads to the fact that at intermediate scales, the two-point function deviates from the perturbation theory, whilst at the UV, they all converge, as the theory is asymptotically free. In the infrared, the flow is cut off by the respective renormalized masses, so you don't see anything. And then, of course, the interesting object to study is the tetrahedral coupling, which I show here, or the inverse of the tetrahedral coupling, which is just given by the simple equation of the wave function renormalization in the ratio to the value of the UV scale. Note that here I'm always plotting everything with respect to P. You might be more used to plotting it with respect to mu, having some external infrared regulator with which I flow. It's the same thing, you just need some scale with which you're probing the system. And it's just, I just use the external momentum as a scale, because it's already what is given to me. But in principle, I could put in some regulator with a mu and just change the mu. Doesn't really matter.
So mu here plays the role of your ultraviolet scale,
yes,
where you start the evolution,
yes,
and P plays the role of the physical scale
of the mu that you used. Yeah, exactly. That's correct. And so the inverse coupling, you see that, first it approaches 1, of course, due to our renormalization at where P is mu, but it importantly also increases, which just reflects asymptotic freedom. And then as you follow this line further down, you would, perturbation theory predicts, which is this dashed line, predicts that there's a zero crossing at some finite scale. This you can just follow it further, and at some finite p square it will cross zero, meaning that the coupling diverges at a finite Landau pole in the infrared. Note that this line is strictly straight, so it just goes down. It's simply this logarithmic running here. And also perturbation theory, the prediction is independent of the mass that you plug in. So you always find the same thing, independent of what your renormalized mass is. However, for us, if we solve these equations, we find two things. First, that the mass cuts off the flow at some scale, some finite momentum scale. It acts effectively as some infrared regulator, which is leads to the coupling leveling off. So the coupling does not blow up for a range of masses. But also note that the coupling becomes steeper. So this is not a straight line here. It keeps increasing, which begs the question of what happens if you send the renormalized mass to zero. And this I will answer in a second. But first, I want to emphasize that the perturbative result is independent of the renormalized mass, and I will always find a Landau pole, whilst in the self-consistent simulation, I find that the coupling always levels off and becomes constant, meaning that the theory is for a range of masses, for the range of masses that I show here, for example, which means that there's a range of renormalized masses for which you can completely solve the theory, all momentum scales, and it's well defined.
So this mass should be interpreted as a common mass for all scalar fields?
Yes, yes.
So it makes sense that when the fields decouple, they stop affecting the self-consistent solution.
Mm-hmm.
I can decouple in the in the infrared the effect of these fields because they are massive.
Yeah.
The effective theory doesn't contain them.
They don't flow anymore.
They don't flow anymore.
Exactly. So
Sorry.
the mass just cuts it off.
So can I say that your scaling organization group running is truncated or
Yeah.
essentially stopped at P of order M,
Yes.
right?
Or I mean, there's some relation between P and M. So in this insight, I show you the momentum scale at which this turns over. So it's related to M, but yeah.
Linear relation.
Yeah. So it's
Right.
basically given by
There's no
M.
other scale, right? Except the Landau pole, which occurs at even more infrared scale.
Yeah. Which begs the
And
question.
therefore
What,
you never get there
yes.
because you're
Except for when you keep decreasing the mass or increasing the correlation length, right? So
of course, you basically, the question is whether your Landau pole is the infrared relative to the mass
yes.
or vice versa.
Yes, exactly. So let me address exactly this point. So what happens? So I just want to fix one statement, namely that there is a range of masses for which you can solve theory for also a range of couplings, and you can have everything accessible and it's strongly coupled with a scale-dependent coupling. However, now the question is what happens is you keep decreasing the mass. What happens? You already see here that this curve becomes more steep, so it seems to suggest that something non-trivial will happen. And let me investigate this now with you. So in the top left, I show you now the coupling, so not the inverse anymore. It keeps increasing as I go to the infrared, to the left. And now I show you a wider range of masses, which I can simulate. It's not quite evenly spaced because I tested out different masses. And here you find that it becomes very small spaced because something non-trivial is happening. First of all, you note that the coupling is larger than the perturbative prediction. And also it seems to increase quicker, which is exactly the statement that the slope is not straight, right? It's become steeper and steeper. Since the perturbative result is predicted to diverge at a finite momentum scale, the Landau pole, this seems to suggest that the non-perturbative result also diverges at a finite scale for a given mass. And this seems to be the picture that we have also now. So this is investigated with this plot here on the right, where I am plotting the infrared value, so the plateau value of the mass, of the coupling, the heterogeneous coupling, versus different masses. So it keeps going up. And then you see here, so and the dashed line is again the perturbative result. And then you see here that there's a range of masses for which the coupling value always lies below the perturbative result, meaning that the theory is well defined, it just levels off, the mass is below above the Landau pole, and it just cuts off the flow, and everything is well defined. However, there's a critical mass, not critical, sorry, wrong word, a mass threshold, m star, below which or around which, as you approach it from above, the coupling keeps increasing drastically, just nearly goes up vertically. And in particular, it crosses the perturbative line. Perturbative line has a divergence at a finite scale. This tells us that there's also a divergence in the self-consistent solution if you approach this mass scale at a finite momentum scale. Now note that these are two different scales. So one is the mass scale, where this phenomenon occurs, that you have a divergence at a finite momentum scale. This m star, it's somewhere here. Yeah, it's given by this 28.6 in these units. And then there's a non-perturbative strong coupling scale at which, for this m star, the coupling diverges, and you can estimate it, or we try to estimate it at least, from the inverse coupling. You can just go, we just extrapolate linearly. It's not quite linear in practice, but as an estimate, as a bound, extrapolate linearly along the envelope of these different curves for different masses, and then look for where this extrapolation crosses zero, right? So as in perturbation theory crosses zero at some scale, which is the Landau pole, and then as you see here, the slope is different, and this extrapolated crosses zero at some smaller scale or larger momentum scale. And this we call mu star. So mu star is at 25 in these units. So you have some range, of scales. You have mu star, the strong coupling scale, m star, the threshold value, and then the perturbative value in practice. And this suggests, and the question is, of course, what happens here, right? Is the theory not well defined anymore if I decrease the mass too far? And I think so. My current understanding or thinking about this is that probably, I mean, the mass keeps increasing as you decrease. So the coupling keeps increasing as you decrease the mass from above, as you increase the correlation length. And what will probably happen is that some bound state formation is triggered. Right? The coupling increases and then bound states will form, which leads to the fact that your degrees of freedom are not the same anymore as in this UV regime. Meaning that bound states are described by composite fields and their effective interaction is generated from quantum fluctuations at higher order. It's not the standard quartic tetrahedral interaction. Whilst in this regime, or in this UV regime, this quartic coupling is the scattering of these unbounded particles, just these tri-fundamental fields, tensor fields. If you simulate the theory as you approach M star, there will be some bound state formation, and then you have an interaction between these bound states. So you have to change the degrees of freedom, and this is not the physical interaction anymore. There will be some other interaction, which will probably be finite and describe this theory. That's what we are thinking currently.
There will be some mass scale or length scale generated.
Yes. I mean, I suspect it will probably relate to this mu star, which is the scale, momentum scale at which it diverges, so similar to lambda QCD, so to speak. And yeah, this we want to now investigate in the future by looking at the 4-point functions, looking at resonances in the 4-point function, these kind of things. Yeah. Okay. So now to close, I want to also talk about the real versus imaginary case, to also go back to that, so discuss what people have done and also comment on the one component field. So left is imaginary, right is real, meaning that I just changed the sign into one of this G² diagram. It's just a sign flip for the perturbative result. This is the for the self-consistent result. This is the perturbation theory prediction for the imaginary case. If you want to have real, you just flip a sign here, go to minus. And in the imaginary case, you see that as we discussed, the coupling grows strong. So your propagator develops some non-trivial momentum dependence, some strong and normalized dimension, which deviates from the even from the perturbative result as you solve self-consistently. In comparison, in the real case, the propagator, the couplings have triviality, so they decrease towards the UV, meaning that the propagator also increases, and conversely decreases as you flow towards the infrared. And as in the imaginary case, you see here that the curves, they're a bit different from the perturbative value because this coefficient is basically resummed to some non-perturbative value. In particular, I also note that in the real case, since it's trivial, you can solve even at renormalized mass 0, and it just shows you what you expect, the perturbation theory result. So it's nothing surprising, but it's good that we can do it. And then, so this is the last my last slide, and just the last important maybe comparison. So this is the real on the bottom and the imaginary coupling on the top, ternary coupling running was momentum scale for different masses, and the perturbative predictions respectively, where I see that first of all, of course, I renormalize the theory, so there's a crossing of the two curves at mu, right? Because I give the value, they have the same value. And then as you go above mu, you see one goes up, one goes down, because one is trivial, one is asymptotically free. And then conversely, you can follow the flow into the infrared, meaning that the imaginary one grows and is cut off by a given mass scale above the threshold mass, whilst the real one just decreases and keeps decreasing, reflecting triviality of the problem.
What is this reference to Szymanczyk?
Yeah, he was the one, okay, this comes here on the right-hand side. He was the one who looked at asymptotic freedom one component scale fields. And this is just this, exactly this is this point, which also Luca made earlier already, that the beta function for one component, single component quartic theory is just quadratic, right? It just comes from the leading order sunset contribution. And then if you integrate this equation, this is the flow of the coupling, the quartic coupling, with some positive constant k here. So then you see here, since it's quadratic, the only way you can achieve asymptotic freedom, I mean, from this you already see that this is trivial. It just decreases as you go towards the infrared. And here you can achieve asymptotic freedom only if you turn the coupling itself negative. And this is exactly the problem, because then the theory becomes unstable. And the difference is to these tensor models is that they are G cubed at leading order, because it's this wave function renormalization which drives the flow in the large n limit. And then you can achieve a negative sign with an imaginary unit, because this is G squared in the denominator. And this is exactly the difference. So, I mean, there was a lot of investigations early on to try to circumvent these bounds on asymptotically free theories and for dimensions. But these failed, so to speak. This is the current understanding.
So is negative worse than imaginary?
Yeah, because they are not bounded. I mean, it's just, I mean, this one is, I mean, it seems to be well defined, I would say. The effective action is real, the path integral is bounded, because you have like two other couplings which are positive, and the imaginary one is just on an oscillatory direction. And if you think of importance, something is just like a non-vanishing baryon density QCD. You just have one oscillatory direction, which you have to, if you do importance sampling, but there's two positive directions which bound the potential. So
But it's imaginary even in Lorentzian signature.
yes.
But suppose we want to check the optical theorem.
Yeah.
Yes.
What, don't you need unitarity
Yeah.
for that? So probability is equal to
Yeah.
1, sum of probability.
Yeah, I understand. I don't know yet. I mean, it's true. This we have to check. I have no results from Minkowski space currently, so I cannot say anything. Since the theory seems to, or maybe this is a good point to summarize. So the theory seems to be well defined at vanishing temperature in Euclidean space, and I think this is maybe this is suggestive or positive evidence that there might be also well-defined theory in Minkowski space after you rotate, because there's nothing violent going on, at least in this range of masses above threshold. So that you can try to investigate this. And this is exactly our to-do list. So what I try to talk about today is that we have like realized an asymptotically free massive scalar field theory in 4 dimensions, which is due to this non-trivial large n limit tractable, analytically in closed form, also non-perturbatively. You can solve it in a computer. And then we find that quantum fluctuations generate a strong coupling that is well defined for all masses above a certain threshold mass. So you can study the theory for all momentum scales if your mass is above a threshold mass for a given coupling in the UV, and you can do whatever you want. You can just solve it. As you approach this threshold mass, we talked about that something non-trivial is happening. And this is my outlook, so to speak. This is what we are trying to investigate now. So first of all, of course, I have not shown you the flow of G1 and G2, which we're solving for now by the beta zeta equations of them two. Perturbatively, they are predicted to already approach a constant, and since G levels off in the infrared, this will probably be similar. And then we want to look for this bound state formation and eventually finite temperature behavior, and then hopefully in the long run, all these very important Minkowski space dynamics questions emerge. What is about unitarity? Is the theory stable in Minkowski space? Do we have a stable equilibrium? Do we have a stable vacuum? And then eventually, hopefully, real-time dynamics with a scale-dependent strong coupling. Can we look for non-thermal solutions? Can we find bounds for transport coefficients and thermalization times with a scale-dependent coupling? Yeah, lots to do. So thank you for your attention.
Since we discussed phi to the 4th theory, I am curious if you can comment on what Polar Maschke is saying.
Yes.
About phi to the 4th theory at large.
So he's
related.
Yes. So he's saying so there's different works of his.
Who's
Paul Maschke. I guess the crucial, so let's say the starting point of these ideas is that there was a paper in 2018 or 19 by Eisenman and others, which proved mathematically that the one component theory is trivial. So quartic phi to the 4th theory is trivial. Does not have a continuum limit. And then Powell argues that there exists a loophole for the standard ON linear sigma models, namely that this only applies, first of all, or the conditions for this to apply is that you have to call positive coupling, okay? And you have to have one component. For multiple components, he claims that this is not the case. And you can solve it, in this large n limit, where you have these daisy resummations, you can solve the beta functions, and he claims that the theory remains well defined. He solved for the correlation functions. He finds that non-trivial behavior, takes place. That the theory seems to be well defined even beyond the Landau pole. There's many things where you have to be careful, but he claims basically that there's just bound state formation at the Landau pole, and then you can continue towards the UV from there onwards. So the theory for finite and a non-one.
Asymptotically free also.
If you turn the coupling negative, yes, which has this problem of boundedness, but then so he and others have some works where this quartic theory, however, is PT symmetric, and then you can make sense of it in this idea by Bender that since it's PT symmetric, it does have real eigenvalues, though, even though the Hamiltonian is non-Hermitian. But then you have to be really careful, how you solve the theory in the path integral language and so on. But they make some very careful arguments, and it seems to be well defined. I don't know.
So the first claim is that there is still a Landau pole, but you have to redefine what you define as the
You have to make a careful analytic continuation.
analytic.
And he looks at the pressure.
My understanding was that what he does is essentially puts Landau pole in the infrared and goes to scales which are more ultraviolet than the Landau pole itself.
And try to define the theory there.
Yeah, that's what I meant. You can go beyond it. That's what I meant. But
No, he doesn't even go beyond that. He's just saying this is in the infrared, and by the time you get there, similar to this massive case.
Yeah, but there's different works though. So there's one work which the coupling is positive, and he just does large N theory, and he shows that the correlation functions are non-trivial. And then there's the work where the coupling is negative, meaning that the Landau pole is now in the infrared because of asymptotic freedom. And then he claims that via PT symmetry and so on, you can still make sense of the theory.
That's what I thought similar to what you were saying.
Yeah. But we don't have these arguments of
hidden in the infrared.
We don't have these arguments of PT symmetry, but the large N effective action seems to be well defined. And since you have multiple couplings, the potential is also bounded.
You don't have those arguments because they're harder to establish, so you can show that they simply know PT symmetry.
The model does not have PT symmetry.
Doesn't have.
Yeah, doesn't. So these arguments don't apply. Doesn't mean that the theory is not well defined. It's just this argument does not apply.
Thanks.
Most.
Yeah.
Oh, you are.
Let's thank again.
Thank you.
You're going to chat?
Yeah.